Hello science fans, welcome you all on ChemistryJungleEdu YouTube channel. Today we are diving into the amazing world of chemistry. But what exactly is a chemical reaction? Well, think of it like this. Imagine you have some building blocks like Legos. You can take them apart and put them together in new ways, right? A chemical reaction is kind of like that, but with tiny particles called atoms and molecules. It's a process where substances, which we call reactants, change into entirely new substances called products. These new substances have different properties from the ones we started with. So, how do we know if a chemical reaction has actually happened? We look for clues, or signs. One common sign is the evolution of a gas. You might see bubbles appearing, like when you drop a fizzy tablet into water. Another telltale sign is a change in color. Imagine something clear suddenly turning bright blue or a shiny metal turning a dull brown. Another exciting sign of a chemical reaction is a change in temperature. Some reactions release heat, making their surroundings warmer. Conversely, some reactions absorb heat, making things feel colder. Alright, future scientists, let's put on our detective hats and delve deeper into spotting these chemical reaction signs. Consider the evolution of a gas. When you add zinc granules to dilute sulfuric acid, you will notice bubbles forming. These bubbles are hydrogen gas. This is a classic example where a metal reacts with an acid to produce a gas. Now let's talk about color changes again because they are so visually striking. Imagine you have a solution of copper sulfate, which is a beautiful blue color. If you drop an iron nail into this solution, you will observe the blue color fading and a reddish-brown coating forming on the nail. The change in color is a direct result of new chemical compounds being formed. What about the release or absorption of heat? When you burn a piece of wood, it's not just the light you notice, it's the heat. Burning or combustion is a chemical reaction that releases a significant amount of energy as heat and light. On the flip side, think about those instant cold packs you use for injuries. When you squeeze them, chemicals inside mix and a reaction occurs that absorbs heat from the surroundings, making the pack feel cold. Observing these signs helps us understand the invisible world of atoms rearranging. Now that we are experts at spotting chemical reactions, how do we describe them efficiently? That is where chemical equations come in. A chemical equation is like a recipe for a chemical reaction. It tells us what ingredients we start with, the reactants, and what new things we make, the products. Instead of using words, we use chemical symbols and formulae. For example, the symbol for hydrogen is H, and for oxygen it's O, water, which is made of hydrogen and oxygen, has the formula H2O. In a chemical equation, the reactants are always written on the left-hand side. Then, we draw an arrow, pointing from left to right. The new substances, the products, are written on the right-hand side of this arrow. To make our chemical equations even more informative, we often include the physical states of the reactants and products. Writing these equations is the first step towards understanding the quantitative aspects of chemistry. Now, writing a chemical equation is great, but there is a very important rule we must follow. It is called the law of conservation of mass. This law, discovered by Antoine Lavoisier, states that matter cannot be created or destroyed in a chemical reaction. The total mass of the reactants must equal the total mass of the products. Atoms are not lost, nor are they magically gained during a reaction, they just get rearranged. This is a fundamental principle in chemistry. So what does this mean for our chemical equations? It means they must be balanced. A balanced chemical equation has the same number of atoms of each element on both the reactant side and the product side. If we write an equation like H2 plus O2 yields H2O, for the formation of water, take a closer look. On the left we have 2 hydrogen atoms in H2 and 2 oxygen atoms in O2. On the right in H2O, we have 2 hydrogen atoms but only 1 oxygen atom. The oxygen atoms are not balanced. This equation, as written, suggests an oxygen atom has vanished, which violates the law of conservation of mass. We need to fix this by placing numbers, called coefficients, in front of the chemical formulae. The balanced equation is 2H2G plus O2G yields 2H2OL. Balancing equations can sometimes feel like a puzzle, but it's a crucial skill. Section 5. Let's combine. Exploring combination reactions. The first type we will look at is called a combination reaction. In a combination reaction, 2 or more substances combine to form a single new substance. The general form for this type of reaction can be written as A plus B gives AB. A classic example of a combination reaction is the burning of magnesium ribbon in air. Magnesium, symbolized as Mg, is a shiny metal. When you heat it in the presence of oxygen, symbolized as O2 from the air, it burns with a dazzling white light and forms a white powder called magnesium oxide, symbolized as MgO. The balanced chemical equation for this is 2Mg solid plus O2 gas gives 2MgO solid. Another common example is the formation of water from hydrogen and oxygen gases, which we balanced earlier. 2H2 gas plus O2 gas gives 2H2O liquid. Understanding these reactions helps us see how simpler substances can build up into more complex ones. Section 6. Breaking up. Understanding decomposition reactions. In a decomposition reaction, a single compound breaks down into two or more simpler substances. The general form for this type of reaction is AB decomposes to give simpler products A and B. Decomposition reactions often require energy to get started. This energy can be supplied in different forms like heat, light, or electricity. When heat is used to break down a compound, it's called thermal decomposition. A common example is heating calcium carbonate, which decomposes into calcium oxide and carbon dioxide gas. The equation is calcium carbonate plus heat yields calcium oxide and carbon dioxide. Sometimes electricity is the key to breaking a compound apart. This is called electrolysis, meaning splitting by electricity. A fantastic example is the electrolysis of water, which decomposes into hydrogen gas and oxygen gas. Decomposition reactions show us how complex substances can be simplified, revealing their constituent parts. Section 7. The swap meet. Displacement and double displacement reactions. In a displacement reaction, a more reactive element displaces a less reactive element from its compound. The general form is A plus BC yields AC plus B. A classic example is when you place an iron nail into a solution of copper sulfate. Iron displaces copper from the copper sulfate solution. The equation is iron plus copper sulfate yields iron sulfate and copper. Next, we have double displacement reactions. In a double displacement reaction, two compounds react, and the positive ion of one compound swaps with the positive ion of the other compound. The general form is AB plus CD yields AD plus CB. A common example is the reaction between sodium sulfate solution and barium chloride solution, forming a white precipitate of barium sulfate. These swapping reactions create a fantastic variety of new substances. Section 8. Hot stuff and cool changes. Exothermic and endothermic reactions. Some reactions release energy, usually as heat and sometimes light, into their surroundings. These are called exothermic reactions. When an exothermic reaction occurs, the surroundings get warmer. Think of a roaring bonfire or the burning of natural gas in your kitchen stove. A very important exothermic reaction happening inside our bodies right now is respiration. During respiration, glucose reacts with oxygen, releasing energy that our cells use to function. On the other hand, some reactions absorb energy from their surroundings. These are called endothermic reactions. When an endothermic reaction takes place, it takes in heat and the surroundings become cooler. A great example is the decomposition of calcium carbonate into calcium oxide and carbon dioxide when heated. Photosynthesis, the process plants use to make their food, is a vital endothermic reaction. Understanding whether a reaction releases or absorbs energy is crucial in chemistry and its applications. Section 9. Reactions in our world, a quick recap, and brain teasers. Chemical reactions are not just things that happen in a science lab, they are happening all around us, all the time. Think about the rusting of iron. When an iron object is exposed to oxygen and moisture, it develops a reddish-brown flaky coating called rust. This is a slow chemical reaction where iron reacts with oxygen and water to form hydrated iron D3 oxide. Consider the curdling of milk. When milk turns sour, it's because of chemical reactions. Bacteria present in milk convert lactose into lactic acid. Even cooking food involves a multitude of chemical reactions. When you bake a cake, the heat causes ingredients like baking soda to decompose, producing carbon dioxide gas that makes the cake rise. So let's quickly recap what we've learned. Chemical reactions involve the transformation of reactants into products, often indicated by signs like gas evolution, color change, temperature change, or precipitate formation. We represent these reactions using balanced chemical equations, which obey the law of conservation of mass. We explored 5 main types: combination, decomposition, displacement, and double displacement. Keep exploring, keep questioning, and keep experimenting safely, of course. Science is everywhere.